Hi students, I am Kailash. So today I will be teaching you what is hysteresis and hysteresis loop. So what is hysteresis and how to draw hysteresis loop for a given ferromagnetic material which is taken through one complete cycle of magnetization. Now this particular topic comes under lesson 3 of 12th standard, magnetism and magnetic effects of electric current. So it's an important 5-mark question. So what is hysteresis and explain how to draw hysteresis loop for a given ferromagnetic material taken under one complete cycle of magnetization. Okay, right. So what is hysteresis first of all? Now let me consider a bar magnet. Let me consider a bar magnet. I can have any pole over here, North Pole, South Pole. I can also have South Pole below and North Pole above. Okay, right. So I can invert the magnet. Now, let me take a small piece of ferromagnetic material, say a piece of steel, okay, closer to the magnet. Okay, so you will notice that the material will be attracted by the magnet. Okay, so now let me call this as a specimen. The steel piece, what I am taking closer to the bar magnet, let me call it as a specimen. So what I have actually done here is I have magnetized the specimen. That is, when I take the specimen, a ferromagnetic material, closer to the bar magnet, it will stick to the magnet. Now the specimen will become a magnet. Okay, how the specimen has got magnetized, or is the specimen has got magnetized? How to confirm that? You take a small safety pin and closer to the specimen. You take a small safety pin closer to the specimen. You will notice that the safety pin will be attracted by the specimen. So which confirms the specimen has got magnetized. Magnetic field is induced to the specimen. Now who is magnetizing the specimen? It's the magnetic field surrounding the bar magnet magnetizes the specimen. So already we have learned in the earlier classes, the magnetic field which is used to magnetize a specimen is called magnetizing field. So what I am going to call the magnetic field around the bar magnet here is a magnetizing field because it's responsible for magnetization of the specimen. Okay, so let me take the magnetizing field around the bar magnet as H. Now once when the specimen is taken in the within the magnetic field of the bar magnet, I just told you it has got magnetized. Magnetic field is induced to the specimen. Let it be B. So H is the magnetizing field strength and B is the magnetic field induced to the specimen. Now what I am going to do is, I am just going to remove the bar magnet, okay, from the specimen. The specimen in the bar magnet detach pannidalam. So I am going to carefully remove the bar magnet from the specimen. I am going to take the bar magnet away from the specimen. So once when I remove the bar magnet from the vicinity of the specimen, what is that actually I am doing is, I am removing the magnetizing field to which the specimen was subjected or which was responsible for the magnetization of the specimen. So once when I remove the bar magnet from the vicinity of the specimen, okay, the specimen is no more within the magnetizing field, or the magnetizing field to which the specimen is subjected to now will be 0. So by removing the magnetic bar magnet away from the specimen, I am nullifying the magnetizing field to which the specimen is subjected to. Now one will expect the specimen to be immediately demagnetized. So once when H becomes 0, one will expect the specimen to lose its magnetism immediately on the spot. But that thing will never happen. You can see the safety pin will be still sticking to the specimen for a certain period of time. It doesn't fall off immediately, which implies the specimen has not lost its magnetic field induced immediately when H is made 0, when the magnetizing field is made 0. Excuse me. Okay, right. Now after some time, the safety pin will get detached from the specimen. So at that stage, we can confirm that the induced magnetic field B in the specimen has reached 0, but little later when compared with H. So if I fix the value 0 as the destination value, H becomes 0 first on the removal of bar magnet. But B induced in the specimen, the magnetic field induced in the specimen doesn't reach the destination value 0 on the spot. B is retained by the specimen for a certain period of time. It is becoming 0 only after some time or little later when compared with H. So thus I can say B is lagging behind H. So H is 0 on the spot. Magnetic field B in the specimen is not becoming 0, rather it is becoming 0 only after certain period of time. That is, B is lagging behind H. So lagging of B behind the magnetizing field H is called hysteresis. So what is hysteresis? Hysteresis is the phenomenon in which magnetic field B induced in the specimen lags behind the magnetizing field, the one which is responsible for the magnetization of the specimen. So when the magnetizing field H is made 0, the magnetic field induced in the specimen will not become 0 immediately, but rather only after some time. So this lagging of B behind H is called as hysteresis. Okay, I will show you a very small demo in it. Okay. So what I have with me is a bar magnet. Okay, wait for a minute. Okay. So what I have here with me is a bar magnet. Can everybody see it? Okay, right. Now, so this is a specimen, a safety pin. Okay, this is the specimen. I'm going to consider this as a specimen. Now we can see the specimen is sticking to the bar magnet. Can everybody see it? Right. So which implies the specimen has acquired magnetism. That is, magnetic field is induced in the specimen. Now who is doing that? It's the magnetic field surrounding the bar magnet that magnetizes the specimen. So I'm going to call the magnetic field surrounding the bar magnet as magnetizing field. Okay. Now how do you confirm the specimen has got magnetized? Now I have one more safety pin here. So let me take it near, not near the magnet, but near the specimen. See, the safety pin is sticking to the specimen. Can everybody see it? Right. So this confirms the specimen has got magnetized. Now let me remove the bar magnet away from the, let me take the bar magnet away from the specimen. So I am nullifying the magnetizing field H. I am making H 0. But if you look at the small safety pin, it is sticking to the specimen yet, which implies the specimen is retaining the induced magnetic field B for a certain period of time. Only after some time, the magnetic field in the specimen will become 0. So who is becoming 0 first? H is reaching the destination 0 first, but B is reaching 0. B will reach 0 little later. It is retaining the magnetic property as long as the small steel piece is sticking to it. Let me shake it. Okay. Now, if I take the safety pin and if I stick to the specimen, you will just notice. Just see. So this is a specimen which has got magnetized, and this was a pin which was sticking to it initially. Now let me take it near the specimen. It is not sticking to it, which implies the magnetic field induced in the specimen has become 0. But both H and B are not becoming 0 simultaneously. H is becoming 0 first and B reaches the 0 value little later. So the word later is called the lagging. So who is lagging here? B is lagging here. Behind whom B is lagging? Behind H, B is lagging. So lagging of B behind magnetizing field H is called hysteresis. Hi students, we will just see how to draw hysteresis loop for a given ferromagnetic material. Or for example, let me consider you are given a small piece of iron, say for example an iron nail. Okay, now what I am going to do is I am going to place the iron nail in a magnetizing field. Once when I place any ferromagnetic material, here it is iron, in a magnetizing field, the specimen, what I am going to call the iron nail as hereafter, the specimen, right? The specimen will be magnetized. That is, it will acquire magnetic field. Magnetic field will be induced in the specimen. So the magnetizing field will induce the magnetic field in the specimen, right? Now what I am going to do is, I am going to increase the magnetizing field strength. So the one who is magnetizing the ferromagnetic material, magnetizing field, அதோட strength I am going to increase. Once when the magnetizing field becomes stronger, the ferromagnetic material, that is a specimen which is subjected to it, will be strongly magnetized. So the magnetic field B induced in the specimen will increase. So increasing the H, the magnetic field will increase. Now what I am going to do is I am going to decrease the magnetizing field. The magnetic field will also decrease. So increasing the magnetizing field will increase the induced magnetic field in the specimen, and decreasing the magnetizing field will decrease the induced magnetic field in the specimen. Right, now the thing is that the variation of B, that is the induced magnetic field, with respect to the magnetizing field H will not be proportional. That is, if I increase H 2 times, I told you when I increase the magnetizing field, magnetic field induced in the specimen will increase. But the increase will not be proportionate. Proportionate increase means if I increase the magnetizing field 2 times, if I increase the magnetizing field 2 times, the magnetic field induced in the ferromagnetic material should also increase by 2 times. If I decrease the magnetizing field by 4 times, the magnetic field induced in the specimen should also decrease by 4 times. They should show the same type of variation. The same variation. Only then I can say they are proportional. So the important point what you should remember is, though B increases or decreases on increasing and decreasing the magnetizing field, the variation of B with respect to H will not be proportional. So whenever two quantities variation are not proportional, if two quantities are not proportional to one another, if I plot a graph between them, I will never get a straight line. I will get a curved line. So the graph between two quantities which vary with respect to one another but not proportionately will not be linear. Linear means I don't get a straight line. For example, if I plot a graph between voltage and current as far as the conductor is concerned, you know, current varies proportionately with respect to voltage. So the graph between V and I will give me a straight line. So we say V and I variation is linear. But B and H variation of B with respect to H, WRT means with respect to H, is not linear. That is, the graph between B and H will never give me a straight line. Rather, it's going to be a curved line. Okay. Right, so B is not proportional to H. For example, if A is proportional to B, then I can write A is equal to some constant times B. And if I bring B to the left hand side, I can say A by B is equal to K, where K is a constant. So whenever A is proportional to B, ultimately I can say the ratio of A to B will always be a constant. So this is true only when A and B are proportional to each other. But B is not proportional to H. B is not proportional to H. This implies B will not be equal to constant times H, which implies B by H will not be a constant. Okay, right. So first of all, you should remember this, don't forget. So whenever I increase or decrease the magnetizing field, the magnetic field induced in the specimen will also increase and decrease, but not proportionately. Therefore, the graph which is plotted between magnetic field induced in the specimen and the magnetizing field will always give me a non-linear trace. That is a curved line rather than a straight line. Okay, so what I'm going to do is step 1. I'm going to take a ferromagnetic material. Let me call it as a specimen. I'm going to subject it to a magnetizing field. So first, the magnetizing field is made 0. And now I increase the magnetizing field slowly. So let me increase the magnetizing field slowly. For each and every values of magnetizing field, let me note down the magnetic field induced in the specimen. So as I told you, when the magnetizing field increases, the magnetic field induced in the specimen will also increase. Now for one particular magnetizing field, the magnetic field induced in the specimen will become maximum. Increasing the magnetizing field beyond that will have no effect on the magnetic field. That is, the magnetic field induced in the specimen will reach its saturation value. So it will not increase further. Okay, right. So now let me put a trace in the graph, the thing what I told you now, the step 1. So in step 1, take a ferromagnetic material, I'm going to call it as a specimen, subject it to a magnetizing field, subject the material to a magnetizing field. First the magnetizing field is made 0 and then I'm going to slowly increase it. When I increase the magnetizing field, the magnetic field gained by the specimen, acquired by the specimen will also increase. And for one particular value of H, it will reach maximum value. Okay, now let me plot this variation in the graph. So what I have done here is I am taking magnetizing field H along x-axis and the magnetic induction developed in the specimen, induced in the specimen along y-axis. Okay, right, now listen. So the magnetizing field is 0. The magnetic field induced in the specimen B will also be 0. Now on increasing the magnetizing field, the magnetic field will also increase, but not linearly. So I will get a trace like this, a curved line, rather than a straight line. 1 minute please. Okay, so I'll get a curve like this. So at the point C, the magnetic field induced in the specimen will be maximum. So I'm going to call the particular magnetic field, that is the magnetic field corresponding to the point B. Let me put a perpendicular line to y-axis. So the point where it meets on y-axis will have a particular value of magnetic field, isn't it? So B max. So at this particular point, the magnetic field induced in the specimen will be maximum. I am going to call this as saturation magnetic field. So for one particular value of magnetizing field H, the magnetic field induced in the specimen reaches maximum. So this is the magnetic field value corresponding to the point C. So I'm going to call this point C as saturation point. I'm going to call this point C as saturation point. Okay. Now what I'm going to do is, now once the magnetic field becomes maximum, now I stop increasing the magnetizing field, because beyond this magnetizing field has no effect on magnetic field gained by the specimen, acquired by the specimen. Now I am going to decrease the magnetizing field. Once when I decrease the magnetizing field, the magnetic field acquired by the specimen will also decrease. But the thing is that the curve will not retrace its path. For example, let me arbitrarily fix a value like this. Say when the magnetizing field is 50, let me assume. When the magnetizing field is, for example, okay, just an arbitrary value. So when the magnetizing field is 50, say the magnetic field in the specimen, let's say 70. So this is during increasing of magnetizing field. Now I am going to decrease the magnetizing field. Once when the magnetizing field reaches the value 50, one may expect the magnetic field in the specimen to become 70 from the saturation value. But it does not. The magnetic field in the specimen during the decrease of magnetizing field, for the magnetizing field value 50, rather than being 70, will be slightly more than 70, say 74. So your curve doesn't, I'm sorry, here, somewhere over here, 74, 50, 74. So if I join C on this particular point, you can see the curve is not retracing its path. Okay, so once the magnetizing field is decreased, the curve will not retrace its path. So due to the property of hysteresis, the ferromagnetic material will retain more magnetic field during the decrease of H than the increasing process, right? So the curve will gradually, the magnetic field will gradually decrease, but following a different path. And once the magnetizing field is made zero, the magnetic field in the specimen will not become zero immediately. It will retain a small value of magnetic field even though H has become zero. So you call the magnetic field corresponding to this particular point as residual magnetism. You call this as residual magnetism. So this particular value corresponds to residual magnetism or remanence. So what is remanence or residual magnetism? Remanence or residual magnetism is the magnetic field retained by the specimen when the magnetizing field is made zero. Right. Now what I am going to do is I am going to increase the magnetizing field in the reverse direction. Once when I increase the magnetizing field in the reverse direction, the magnetic field will decrease and will become zero for one particular value of magnetizing field applied in the reverse direction. Okay, so let me name this point as D and this as E. So at the point E, for a particular value of magnetizing field H, at the point E, the residual magnetism or the remanence, that is the magnetic field retained by the specimen, first becomes zero. So this particular magnetizing field applied in the reverse direction, let me take it as minus H, right? So that's what I mean by minus H. Minus H, the magnetizing field in the reverse direction of apply control. We are changing the direction of magnetic field. Okay, right. So at the point E, for the particular value of H, the magnetizing field will become zero. The remanence or residual magnetism will become zero. So this magnetizing field applied in the reverse direction is called coercivity. So coercivity is the value of magnetizing field applied in the reverse direction for which the residual magnetism retained by the specimen becomes zero. So the portion AD refers to residual magnetism or remanence and the portion AE refers to coercivity. Now again I am going to increase the magnetizing field beyond this coercivity value. Now the magnetic field developed in the specimen will increase but in the opposite direction, like this, and reaches a saturation value at the point F, which will be same as that of B max over here. Okay. Now once the magnetic field induced in the specimen becomes maximum saturation point, so from there on I will be decreasing the magnetizing field. I will be making it zero, and again I will be increasing it and I will make it H. So once the magnetic field induced in the specimen becomes maximum in the reverse direction, so what I will be doing is I will be decreasing the magnetizing field applied in the reverse direction. I will make it zero, and then again I will increase the magnetizing field in the positive direction up to H. Now you will get a curve like this. So when I do this, I will get a loop like this. So the magnetic field name panikalam first. So let me take it as G. Already H is there. Let me take the sign. So from H onwards, if I decrease the magnetic field to 0 and if again increase the magnetizing field up to H, the curve, the magnetic field or the curve will follow the path F, G, I and C. Now this complete loop what you have got, a curve what you have got is called hysteresis loop or hysteresis curve. Is it clear? Right? So the magnetizing field is made, the magnetizing field is increased from 0. You get the path AC. The magnetizing field is decreased from H to 0. The curve doesn't retrace its path. It takes up a path CD. When the magnetizing field H is 0, the magnetic field B in the specimen doesn't become 0. So we call it as residual magnetism. To nullify the residual magnetism, I am going to increase the magnetizing field in opposite direction. So the magnetizing field which is applied in the reverse direction, which will nullify the residual magnetism, is called coercivity. And from there on increasing the magnetizing field, the magnetic field in the specimen will become saturation, will reach the saturation value in the reverse direction. And from there on, if I decrease the magnetizing field and make it 0, and again if I increase it in the positive direction, the magnetic field or the curve will follow the path F, G, I, C. So this complete loop is called hysteresis loop. So whenever I subject a ferromagnetic material to a magnetizing field which varies like this, 0 to H, positive H to 0, 0 to negative H and negative H to 0 and 0 to positive H once again. So I say that the ferromagnetic material is taken through one complete cycle of magnetization. So when the ferromagnetic material is taken through one complete cycle of magnetization, so I get a hysteresis loop like this. Is it clear? Okay, so that's all. I will give a small recap on the hysteresis loop curve. Yeah, I am going to call it as a BH curve, B-H curve, because it's the graph what is drawn between the magnetizing field and magnetic field induced in the specimen. So whenever a ferromagnetic material is taken through one complete cycle of magnetization, that means if I say the ferromagnetic material is taken through one complete cycle of magnetization, it means the magnetizing field to which the specimen ferromagnetic material is subjected to is varied from 0 to maximum in the positive direction. And the magnetizing field is made 0 again. So let me put it as H max, right? And from H max to 0. And I have to increase the magnetizing field in the reverse direction. So again 0 to negative H. So for one particular magnetizing field, the magnetic field will become maximum. The magnetic field induced in the specimen will become maximum. So let me call that particular magnetizing field as H max and the magnetic field induced in the specimen as saturation magnetic field. Okay, right. Again, I have to decrease the magnetizing field applied in the reverse direction and I have to make it 0. And again from 0, I have to take it back to the maximum magnetizing field in the positive direction. So when I subject a ferromagnetic material to such a varying magnetizing field, I say that the ferromagnetic material is taken through one complete cycle of magnetization. One complete cycle of magnetization. Okay, so during the first step, the magnetic field will increase from 0 to B max. And during the second step, the magnetic field, when I decrease the magnetizing field from H max to 0, the magnetizing field induced in the specimen will change from B max, that is the saturation magnetic field, to not 0. Because when H is made 0, the magnetic field induced in the specimen will never become 0. It will retain a small magnetism for some time. So let me take it as some B. Now, when I change the magnetizing field from 0 to negative H max, so during this process, the magnetic field B retained in the specimen will first become 0, and then for negative H max it will reach the saturation magnetic field but in the reverse direction. And again when I change the magnetizing field from minus H max to 0, the magnetic field induced in the specimen will change from minus B max not to 0 but to a particular value, say B. Because when magnetizing field is made 0, the magnetic field won't become 0 because of hysteresis. Now again if I change the magnetizing field from 0 to H max in the positive direction, the magnetic field will change from the residual magnetism, what the specimen has retained, will first become 0 and then the magnetic field will become maximum. So this is what is going to happen to the magnetic field retained in the, this is what is going to happen to the magnetic field induced to the specimen when the material is taken through one complete cycle of magnetization. Now this variation between H and B when plotted in a graph will look like something like this. I will draw the graph, I will plot the graph, just listen, I will plot the graph because it's a very important 5-mark question. So what I am going to do is I am going to take all the magnetizing field values along x-axis. And the magnetic field induced the specimen along y-axis. So first we will plot the graph for H changes from 0 to H max. Okay? The graph between B and H will be non-linear. So this is H max applied to the positive direction. So the point C corresponds to maximum or saturation magnetic field. I am going to call it as saturation point. Okay, now I am going to decrease the magnetizing field from H max to 0. The curve doesn't retrace its path. It takes up a different path. Okay, right. So C, D. So the magnetizing field is made 0. The magnetic field is retained for some time. So this value of magnetizing field, let me take it as A here. Okay, right. So this value of magnetizing field, I am going to call it as residual magnetism, or in other words, remanence. Now the third step, the magnetizing field is increased in the reverse direction from 0 to minus H max. So the magnetic field will increase in the opposite direction. It will increase in the opposite direction. By doing this, it has to cross the value 0. So for one particular value of the magnetic field, magnetizing field in fact applied in the reverse direction, the magnetic field induced in the specimen will become 0 first. Okay. So at the point E, the residual magnetism or remanence becomes 0 first. So this value of magnetizing field applied in the reverse direction is called coercivity. You are going to call coercivity. So each and every each and every term is 2-mark oriented definitions. So define residual magnetism, define coercivity. Right? So this is the direction of the curve. Now I am going to increase the magnetizing field up to minus H max. So the curve will reach the saturation point, which will be same as before. Should be symmetric. E, F. Okay, right. So this is the direction. Now I am going to decrease the magnetic field applied in the reverse direction up to 0. So the curve will follow this path. The path FG. So once the magnetizing field becomes 0, there will be a small magnetic field retained in the specimen, remanence. Okay, right. Now the magnetic field will be, magnetizing field in fact, is increased from 0 to H max once again. Now the magnetic field in the specimen will increase in the positive direction. So while doing so, it has to cross 0 for one particular value of the magnetizing field, which I am going to call it as again coercivity, I. And then it meets the point C. So this is what we call it as hysteresis loop. So this is what we call it, so this variation when a ferromagnetic material is taken through such a varying magnetizing field, I say the ferromagnetic material is subjected to one complete cycle of magnetization. Okay. Now, what happens when the material is taken through one complete cycle of magnetization? Now, when the material is taken through one complete cycle of magnetization, the molecular magnets, in a ferromagnet, we have studied properties of ferromagnetic materials. Each and every atom or molecule in a ferromagnetic material will possess dipole moment. When I subject a ferromagnetic material to an external magnetic field, the atomic dipoles or the molecular dipoles of the ferromagnetic materials will align themselves in the direction of external magnetic field. That's what we saw in the properties of ferromagnetic material. So here we are subjecting a ferromagnetic material to a varying magnetizing field, not only in magnitude but also in direction. So once when a ferromagnetic material is taken through one complete cycle of magnetization, once when a ferromagnetic material is taken through one complete cycle of magnetization, the molecular magnets in the material, the atoms or molecular magnets in the ferromagnetic material will orient and reorient themselves several times along the direction of external magnetic field. External magnetic field or direction la unga molecular magnets enna avunga orientation agum, magnetizing field reverse agumbodhu orientation ana molecules reverse direction la orientation agum, opposite direction la orientation agum. So like this, the molecular magnets will wobble back and forth. They will orient themselves and reorient themselves several number of times. So due to this orientation and reorientation, energy will be given out in the form of heat, which implies whenever a ferromagnetic material is subjected to a varying magnetizing field, there is always going to be a loss of energy in the form of heat. So this loss of energy in the form of heat is given by the formula, if I say delta E to be the energy lost during one complete cycle of magnetization, then the formula for loss of energy in the form of heat, why the energy is lost in the form of heat? Because the molecular magnets are subjected to a varying magnetizing field, a varying magnetic field in both magnitude and direction. So they get oriented and reoriented several times in different directions. Molecular magnets, each and every molecular magnet, they behave like a magnetic dipole. Magnetic dipole, external magnetic field rotate ஆயிட்டே இருந்தா, oscillate ஆயிட்டே இருந்தா, அதோட potential energy என்ன ஆயிட்டே இருக்குங்க, vary ஆயிட்டே இருக்கும். The variation of potential energy will give rise to heat energy. Okay, so the loss of energy in the form of heat is given by the formula integral, closed integral, H vector dot dB vector. And the numerical answer what I am going to get after integrating this term will be equal to area of the hysteresis curve. So the energy lost during one complete cycle of magnetization of a ferromagnetic material will be equal to area of hysteresis loop. Area of hysteresis loop. So the loop is broader, the area will be more, loss of energy will be more. If the loop is thinner, narrower, then the loss of energy is going to be small and hence, the area of the hysteresis loop is going to be small and hence smaller will be the loss of energy. So that's all for hysteresis loop. Thank you.